An ordinary evening. You're gazing at the star-filled sky, just as our ancestors did thousands of years ago. Calm, eternal, infinite. Now imagine that one of those tiny pinpricks of light isn't a star. It's moving. And with each passing night, it grows brighter and brighter. At first, it's just a curious object for amateur astronomers. Then, it's news in scientific journals. After that, it becomes the main topic on every television channel worldwide. That pinpoint of light is a giant asteroid, several kilometers wide, and it's hurtling straight towards Earth. This isn't a Hollywood blockbuster script. It's a very real, though unlikely, threat that humanity is preparing for right now. What will we do when that day arrives? What are our options? Let's explore. To start with, we need to understand the threat from space is not fiction. We live at the bottom of a cosmic shooting range, and sometimes we do get hit. In 2013, a meteor exploded over Chelyabinsk, a mere 6-story building in size. Its power was 30 times greater than the bomb dropped on Hiroshima. The shockwave shattered windows in thousands of buildings, injuring over 1,500 people. And yet, that was a mere trifle. In 1908, something far more powerful occurred in the area of the Podkamennaya Tunguska River. The blast leveled forests across an area of 2,000 square kilometers. That's larger than the territory of modern Moscow. And that, according to modern estimates, was an object merely between 50 and 100 meters in diameter. Now imagine something the size of an entire city is heading our way. The consequences of such a collision would be not local, but global. And the word apocalypse would cease to be merely a figure of speech. Before we get into the rescue plans, I'd like to ask you to subscribe to the channel. It motivates me to make new videos. Let's quickly get our terms straight. What flies in space is an asteroid, a minor planet. When this rock enters Earth's atmosphere and starts to burn, that's a meteor, or a shooting star. And if a piece of it makes it to the surface, that's already a meteorite. We're particularly interested in asteroids, and not just any of them. Astronomers keep a close eye on so-called potentially hazardous objects. These are asteroids larger than 140 meters, whose orbits intersect Earth's orbit at a dangerous distance. To this day, several thousand of them have already been discovered, and this list grows every year. The good news is that none of the known large asteroids pose a threat to us in the next 100 years. The bad news is, we've discovered far from all of them. It's especially difficult to spot dark asteroids that don't reflect sunlight well, or those coming at us from the direction of the sun. So the early warning system is our first and foremost line of defense. Telescopes around the world, such as Pan-STARRS in Hawaii, scan the sky day and night, tracking the slightest movements. As soon as a new object is detected, scientists begin to calculate its trajectory. This is an extremely complex task, requiring consideration of the gravitational influence of the sun, planets, and even other asteroids. But if we're talking about a planet killer, then we'll most likely spot it years or even decades before impact. And that time is our most valuable resource. The clock has started ticking. What's our plan of action? The first thought that comes to mind, inspired by countless movies, is to blow it to smithereens. Send a rocket with a nuclear warhead to the asteroid and blast it into tiny pieces. That sounds simple and effective, but in reality, this is perhaps the riskiest and most unpredictable option. Imagine a single large bullet flying at you, and you, instead of dodging, shoot at it with buckshot. Now, instead of one bullet, a cloud of scorching radioactive shrapnel is heading your way, which would cover a much larger area of the planet. To completely destroy the asteroid is incredibly difficult. Most likely, we would simply turn one giant problem into 1,000 smaller problems, making them radioactive in the process. But nuclear weapons also have a more elegant application. This is what's known as standoff detonation. The idea is to detonate the nuclear device not on the asteroid's surface, but at some distance from it. A powerful stream of energy and neutrons will instantly vaporize the part of the asteroid's surface facing the explosion. This vaporized material, flying off into space, will create a reactive thrust, much like a rocket engine. gently but forcefully pushing the asteroid aside. This is no longer a crude sledgehammer blow, but a precise and powerful impulse. The earlier we do this, the smaller the impulse required for the asteroid's trajectory to deflect by millions of kilometers, allowing it to safely pass by Earth. This method is considered one of the most reliable for truly large and dangerous objects, especially when time is running short. But what if we have time and want to avoid nuclear risks? Then another method takes center stage: kinetic impact. This is essentially a game of cosmic billiards on a planetary scale. We send a heavy and very fast robotic projectile spacecraft toward the asteroid, which crashes into it at full speed. The goal isn't to destroy it, but merely to slightly alter its speed. You might think that a collision between some spacecraft weighing a few hundred kilograms and an asteroid weighing millions of tons is like a mosquito bite to an elephant, and it is. But in space, different rules apply. Even a tiny change in velocity, say, by 1 millimeter per second, over the asteroid's years-long journey, will turn into a deviation of thousands upon thousands of kilometers. And this is no longer a theory. On September the 26th, 2022, humanity, for the very first time in history, intentionally altered the trajectory of a celestial body. NASA's mission, called DART, Double Asteroid Redirection Test, successfully slammed into the asteroid Dimorphos, which was orbiting the larger asteroid Didymos. The refrigerator-sized craft collided with the 160-meter Dimorphos at a speed exceeding 22,000 kilometers per hour. The impact turned out to be even more effective than scientists had anticipated. It not only altered the asteroid's speed, but also blasted out an enormous cloud of debris, which then acted like an additional jet engine, amplifying the effect. DART proved we can do this. We possess the technology to knock a cosmic bullet off its deadly course. But what if the asteroid is too brittle and it could break into pieces on impact? Or if we need to alter its orbit with pinpoint accuracy? For such cases, there's an even more elegant solution: the gravity tractor. According to the laws of physics, any two objects with mass attract each other. Yes, even you and your smartphone are attracting each other right now. It's just that this force is infinitesimally small. But in space, in the absence of friction, even the weakest forces can work wonders. The idea behind the gravity tractor is to send a sufficiently massive spacecraft to the asteroid and simply leave it hovering nearby. The spacecraft won't touch the asteroid. It will fly alongside it, constantly running its engines to avoid falling onto it. But its own gravity, however weak it may be, will slowly but inexorably pull the asteroid along with it. It's like a tiny tugboat that for years pulls a giant ocean liner with an invisible gravitational tether. This method takes a very long time, decades, but it's incredibly precise and controlled. We can tow an asteroid to any safe orbit with utmost precision. This is the ideal option if we detect a threat early and want to resolve the problem with utmost gentleness, without any explosions or collisions. Of course, engineering thought doesn't stop there. There are also more exotic concepts. For example, laser ablation. You could direct a powerful laser beam at an asteroid from a ship or even from Earth. The laser would vaporize material from its surface, creating that very same reactive thrust. Or you could use gigantic concentrating mirrors to focus sunlight onto the asteroid and literally burn a rocket nozzle into it. There's also an idea that's utterly brilliant in its simplicity. What if we painted an asteroid? It sounds like a joke, but behind it lies real physics, the so-called Yarkovsky effect. The thing is, dark surfaces absorb more sunlight and heat, while light surfaces reflect more. As an asteroid rotates, its sun-heated side cools down, radiating heat into space. This thermal radiation creates a tiny but constant impulse that pushes the asteroid. If we paint one side of an asteroid white, or cover it with a light-reflecting material, we'll disrupt this thermal balance. One side will be pushed away from sunlight more strongly than the other. Over decades and centuries, this minuscule photonic nudge can significantly alter the asteroid's orbit. It's the slowest, but also the most elegant method of all. But let's be realistic. What if we detected the threat too late? What if all our attempts to deflect the asteroid failed? Humanity must also have a plan B, and this plan is no longer about prevention, but mitigation. Knowing the precise time and location of impact, and modern calculations allow us to determine this with precision down to several kilometers. The primary objective will be a mass evacuation. This will be a logistical operation of a scale unprecedented in history, relocating millions, or perhaps even tens of millions of people, creating temporary shelters for them, providing food and water. If an asteroid were to fall into the ocean, the main threat wouldn't be the impact itself, but a mega tsunami. Waves hundreds of meters high could crash onto the coastlines of entire continents. In that scenario, all coastal cities within a radius of thousands of kilometers would have to be evacuated. But the most terrifying consequence of a truly massive object's impact is an impact winter. So much dust, soot, and ash would be thrown into the atmosphere that they would block out the sun for months, even years. The planet would cool dramatically, crops would fail, and ecosystems would be disrupted. This would be a global catastrophe that would set civilization back centuries, if it didn't outright destroy it. And preparing for such a scenario is practically impossible. So what's the final word? We live under a perpetual yet improbable threat. But we are no longer helpless dinosaurs, staring up in astonishment at a fireball in the sky. We are an intelligent species that has learned to gaze into space, understand its laws, and even intervene in them. We have telescopes to spot the enemy from afar. We have rockets to reach it. And we have an entire arsenal of ideas, from the brute force of a nuclear explosion to the elegant gravitational tug, to make it veer off course. The primary condition for our survival is unity and foresight. Asteroid defense programs require international cooperation and constant funding. This is our collective insurance against the worst natural disaster imaginable. We must keep watching the stars, not just with wonder, but with close attention, because in this cosmic lottery, we cannot afford to lose.